This picture shows the 155 different orbits the Solstice mission around Saturn took, and it uses this topic called orbital mechanics. Now it does look pretty crazy, but we're not going to do anything quite that difficult, but we want to look at just some of the basic stuff about planets orbiting stars or satellites orbiting the Earth. So the first thing we want to do is kind of do with satellites orbiting the Earth. The International Space Station takes 93 minutes to make one lap around the Earth. And you can see that the space station is pretty close to the surface, relatively speaking. Much further away, like the distance of the moon, it takes 27.3 days for the moon to make one lap around the Earth. So the closer something is to the Earth, the shorter time it takes to go around, and the further it is, the longer it takes to go around. So we have these communication satellites, and they're fixed to the ground, pointing up in the sky, looking at a very specific spot in the sky. So what is up there that it's looking at? Well, it's a satellite, of course, but the satellite couldn't just be sitting there. If it was stationary and gravity is pulling the satellite down, well, that satellite would just fall straight into the surface of the Earth. Okay, so that doesn't work. It has to be orbiting so that as it flies tangentially, it misses the Earth. But if it's in a low Earth orbit, it's going to go around the Earth faster than the Earth is going around. And the satellite would only catch a glimpse, or that satellite dish would only catch a glimpse of that occasionally. So what we got to do is we got to place that satellite further away, because further away from Earth it takes longer to go around. And if you place it at just the right distance, it will take 24 hours to go all the way around the Earth, and the Earth goes all the way around in 24 hours. It's called a geosynchronous orbit. And what we want to do here is go ahead and calculate where to place this satellite. I know it sounds difficult, but you really do have all the pieces necessary. When we first started talking about applications of circular motion, I said we had to go on a hunt and find an equal sign. Well, here it is right there. The big trick about this is that the force of gravity equals the centripetal force. The force pulling the satellite toward the Earth is the force that's pulling the satellite into a circle. And for all of these, we are going to do it as if it's a circular orbit. Simplifies things greatly. You would really need some calculus to be able to do it with elliptical orbits. So right now, we're just doing it with circular orbits, and a lot of things orbit pretty close to a circle, so we're not too far off. Well, if we know that the force of gravity equals the centripetal force, that's the Universal Gravitational Equation that calculates how much force of gravity there is. It's the mass of the Earth, the mass of the object, in this case the satellite, divided by the distance between them squared, and then the universal gravitational constant, which is 6.67 times 10 to the negative 11. And then the centripetal force is, the centripetal acceleration is v squared over r. When I multiply it by the mass of the object, well, that's how much force must have been put on it. What's nice here is you can see something cancels out. The mass of the object. This satellite, doesn't matter how much mass it has, it will take the same amount of time if it's at the same distance. Now remember, we're trying to figure out how much time, we're trying to figure out the radius, but we want the time, the period, to be 24 hours, which is 86,400 seconds. And this equation doesn't have time in it yet. It has velocity, but one trick that we got to do is to turn a distance and a time into a velocity, or maybe the other way around. Turn a velocity into a distance and a time. One thing I just showed was that the square here, there's an r times an r on this side, and there's an r there. They cancel. All right. So this just simplifies down into g, mass of the Earth, the radius, and then the velocity squared. So here's what I'm talking about when I was saying we got to turn velocity into a distance divided by the time. You recognize 2 pi r as the circumference, or the distance all the way around. And then this is capital T, or the period, the time all the way around. So we're just substituting that in for velocity. Remember that trick. That's a good one. That distance all the way around, circumference divided by its period, gives you the velocity, the tangential velocity. All of that needed to be squared, so there's 4 things in there. Each of those things need to be squared. So we square the 2, we get 4. We square pi, pi squared, r squared, and t squared. So all of that was just squaring everything inside there. And let's see if we can simplify some things here now again. An r down here would cancel. Sorry, it wouldn't cancel. We have to multiply both sides by r to get this r out of here. Multiply this side by r, it cancels. Multiply this side by r, we get r cubed. And then I'm going to divide both sides by g and the mass of the Earth. They'll show up in the denominator right there. So there it is. That there is known as Kepler's third law of planetary motion. That if you take the time it takes to go all the way around, square it, and it's going to be proportional to the radius cubed, because all of these things are constants. 4 is a constant, pi, g, and the mass of the Earth, all those are constants. So just the period squared is proportional to the radius cubed. It equals if we go ahead and plug in what those things are. So if we go ahead and plug in what those things are, I should say here that g has units that are in mks units, and which means we have to measure the time in seconds and we have to measure the mass in kilograms. When we do that, we would find a radius in meters. So solving this equation for r, we would get 42 million meters is how far that satellite would have to be out away from Earth. So that took a time of 86,400 seconds. That's 26,200 miles out there, which is from the center of the Earth to the center of the satellite. Now, the radius of the Earth is about 4,000 miles. So if you were talking about not center to center, but from surface to surface, it'd be about 22,200 miles from the surface of the Earth out to there. And if you do that, it's going to take exactly 24 hours for that satellite to go around the Earth, and the Earth goes around every 24 hours. It would be in geosynchronous orbit. That 26,200 miles is the same thing as 6.63 times the radius of the Earth. So those satellites are way out there. The International Space Station is just, right in here somewhere, and those satellites are way, way further out there. And then the moon is a lot further than that, of course. Well, we kind of looked at earlier in the previous video about finding the mass of the Earth. And once we knew what the universal gravitational constant was, we could find the mass of the Earth. This equation is not on your equation sheets, but the idea of being able to set the centripetal force equal to the gravitational force, you could be expected to come up with that equation on your own. But knowing how far the Earth is from the Sun, that's this distance, and the time that it takes to go around, you can find the mass of the Sun, which is amazing. We don't want to put in miles and days. We do want to stick with MKS units. So that many miles is this many meters, and that many days, hours, minutes, and seconds is that many seconds. You might think, well, how do we know the distance the Earth is from the Sun? That's actually been known since 250 BCE. And in my last video on universal gravitation, I briefly talked about Aristarchus and how he measured it, and then it was refined over the centuries. If instead of a satellite orbiting the Earth, it was a satellite orbiting the Sun, the derivation would all be exactly the same, except this time would be the mass of the Sun in there. So, we could plug in different things there. And remember that the satellite, if we plug the Earth in there instead of the satellite, the Universal Gravitational Equation takes the mass of the sun and the mass of the Earth, but we also have the mass of the Earth over here, so it cancels. It wouldn't matter if we put a satellite right there or the Earth right there, it would still take the same amount of time to go around. But all I'm really suggesting here is that the only thing that's different is that you would plug in the mass of the sun there. This equation here assumes that the mass of the thing out there isn't quite big enough to cause this thing to wobble. And I'm showing the sun wobbling right here way more than it actually would because of the orbit of the Earth. But if the Earth orbits and it had a big enough mass to really move the thing in the center there, the orbit of that would be a little smaller because that was kind of shifting away from it as it was moving. And the radius would be a little bit smaller. And if we had something really big out there, like another sun, then they would just be orbiting each other in an orbit half the size. So when you see Kepler's third law like this, it's assuming that the thing that is orbiting it is much smaller than the thing it is orbiting. And if you get really big, we have to adapt the equation. It's the mass of one thing and the mass of the other to adjust for the fact that it really wobbles when you have two stars there. All right. Sagittarius A star is a supermassive black hole in the center of our galaxy. And it's about 4 million times the mass of our sun. It's supermassive. But it's the same thing. We can find the mass of that thing if we could look at things that orbit it. And these are several different stars that orbit that black hole. And these are very much elliptical orbits. So this would be the average radius and the time it takes to go around. But by analyzing the orbits that go of these stars that go around Sagittarius A star, you can figure the time it takes a planet to go around and the average radius. You can find the mass of Sagittarius A star, which is really cool, way far out there, but we can figure out how much mass it has. One of the neat things about orbital mechanics, and hopefully it's on the horizon in the not too distant future, is a space elevator, where we can just, instead of taking a rocket to space, we can just get in an elevator and be hoisted up to space. Well, how do you do that? You know, the tallest building is far, far, far shorter than that. So how do you create something stable there? Well, what it is, it's very similar to just someone circling around like this. If this is the Earth circling around and you have a mass tied to a string, rope or a cable, that cable can become quite taut. That the cable there is just pulling against the inertia of the thing swinging around. And that's what happens here. To have a space elevator, you have a satellite a little further than that 6.63 Earth radii, and that satellite would drop a cable down to Earth, you would attach it there, and then the whole thing would just swing around like this, just like that chair swing being whirled around. It's not going very fast, but it's way out there. And because it's further than that geosynchronous orbit, that cable is pulling with additional force, pulling that into a circle. And that cable could become quite taut, and you could climb up that thing. You could take a rocket and just hoist it up some distance and then launch it from there, and you could save tons of fuel, tons of expense. And the real trick right now is getting a cable that's strong enough to do that. And the carbon nanotubes are the things that are on the horizon that just need to be produced in mass quantity to make that work. All right, now there's something they're called Lagrange points. And a Lagrange point is a position or a location in space where you could place an object and it would be in a stable orbit. It would stay in the same spot between the Earth and the Sun. So if the Earth is orbiting around this path right here, you could place like a big old umbrella there. What I mean is, with climate change, you could put like a very large structure at a spot there, and it could block some. You don't want to, of course, block all the light of the sun, but you could place an object there, and it would block a certain percentage of the sun and cool Earth back down to a reasonable temperature. Basically a big sun shade. Well, let's see if we can calculate where we would need to put that. As the Earth orbits the sun, the Earth would move from here to there, the shade would move from there to there. They would have, in the same amount of time, they would have the same tangential velocity, but they would have, I said that wrong, they would have different tangential velocities, but they would have the same angular velocity. And before we said the centripetal force was mass times the tangential velocity squared divided by the radius, but when we're using angular velocity, it's mass times radius times angular velocity squared. So we need a centripetal force pulling that thing into a circle that causes it to go around angularly just as fast as the Earth does. So we want to calculate what the radius of this shade should be. How far from the sun should that be? Well, we know how far the Earth is from the sun. And using the Universal Gravitational Equation, we can calculate the gravitational force that the sun would put on that shade. Okay, and we can also calculate the gravitational force the Earth would pull on that shade. So the sun is pulling the shade that way, the Earth is pulling the shade that way. Even though the sun has much more mass than the Earth, the shade would be further from the sun, so it's not much more force. You do want more force from the sun than from the Earth, so that there's a net force toward the sun. If you take the force of the gravitational force of the sun, subtract it from the gravitational force of the Earth, that would be the net force, which is the force that's pulling it into a circle. All right, so there it is. I'm not going to try to solve that equation from you. It looks pretty scary, and yeah, you'd have to be on your algebra game to solve this. But let's see if anything simplifies out. There's the mass of the shade on this side, there's the mass of the shade here, and the mass of the shade there. It all cancels out. Let me remind you that this is the Universal Gravitational Equation. That's G m1 m2 divided by r squared. So that was just the force of the sun. This is the same thing, m1 m2 over r squared. We had to take the radius of the Earth minus the radius of the shade. The radius of the Earth minus the radius of the shade is how far the shade is from the Earth. But then we would just figure out and solve this equation for the radius of the shade. Everything else in there we know. And you could put that shade right there, and it would stay where it's at. There's a few more variables that I'm not talking about now, like the solar wind, these ionized particles that are colliding into that, so you'd have to account for that. But it's a start. It just helps us begin to understand orbital mechanics. And so this is the sun and the Earth. This is called Lagrange point number 1. Doing the same thing we did, you could find that there's also a place over here and there and there and there where you could place things, and it would stay in that same relative position because the net force between the sun, that object, and the Earth and that object, the net force created a centripetal force that moved it into a circle. Okay, so these objects would just move into a circle as the Earth and everything rotated around. So it's going to seem like I'm diverging here, but I will come back here momentarily. But the Earth has a molten core of iron, and that rotates around and creates a magnetic field. And that magnetic field actually shields us from a lot of these charged particles that are being blasted off by the sun. So this is the magnetic field of Earth, and here's the solar wind, and it deflects those things all around like that. It will actually kind of channel some of those particles in toward the poles, and that's what causes the aurora borealis. But our magnetic field shields us from a lot of that radiation from the sun. Mars does not have a molten core, so it doesn't have that shield. And whatever atmosphere Mars does have, it does tend to get kind of blown away by the solar wind. So if you could terraform Mars, like get a stronger atmosphere on it, and then you'd have the greenhouse gases that would warm up the planet and melt perhaps the water that's on it. But so here's Mars, the sun is over here. You could put a magnetic field right here at a Lagrange point so that it stayed in perfect position between the sun and the Earth. You could put a magnetic field right there, and it would shield Mars from the solar wind, and you could terraform Mars by creating an atmosphere. Now, how strong of a magnetic field would you have to put there? Doesn't actually take that much. Your typical MRI machine in a hospital, the magnetic resonance imaging machine in a hospital, would produce a magnetic field large enough or almost large enough to do just that. So wow, the technology is there. We need a willpower to do it. Okay, so that was just some of the orbital mechanics stuff. A couple more things here. I want to talk about gravitational fields. So a gravitational field is a way of describing the property of the space surrounding mass. Now, mass creates gravity, and puts force on other masses. So the property that we're talking about is that space will now put force on other masses. And so just kind of describing the relationship between a force and a field. If there's no gravitational field, there would be no force on masses. And conversely, if there were no force on masses, there would be no gravitational field. Newton thought that gravity permeated and diffused through space, that gravity shone out there like a light bulb. But Einstein was able to show that gravity does not diffuse through space. Gravity is the space itself. The presence of Earth's mass warps the space around it, and the space now puts force on other masses. So this is the equation we're using to calculate the gravitational field, a way of describing that. So to calculate the gravitational field, it's just how much gravitational force there is per mass. Well, force divided by mass is acceleration. The strength of the gravitational field is the acceleration of gravity. Okay. Now, if I had a small mass out there, there'd be a small force on a small mass, so there'd be a gravitational field. If I put a larger mass, there'd be a larger force on that larger mass, and it'd be the same gravitational field. In fact, everywhere at the same distance from Earth like this, it would have the same property of space. It would have the same gravitational field. All right, so the gravitational field is saying that there is a gravitational force on a mass. The strength of the field is how much force there is per mass. So we'd measure the force in newtons, and we'd measure the mass in kilograms. Okay, which turns out to be an acceleration. So at Earth's surface, the gravitational field is 9.8 meters per second squared. Twice the distance, there'd be 1/4 the force, so the gravitational field would be 1/4 as much. Okay, just describing the property of space, that space puts a force on other masses. This is how we calculate the gravitational force. Yeah, that's how we just what I said. All right, this one's kind of a doozy. it's going to get a little mathy. If you're in AP Physics, this is fair game. If you're in regular physics, probably wouldn't see one quite this hard. But it says this planet here, has a density that is 3/2 that of Earth's, and its radius is twice that of Earth's. What is the gravitational field of this new planet at its surface? So we have, it gave us the density, the Greek letter rho, the density of Earth, and the density of, and the radius of Earth. The density of this planet is 3/2 the density of Earth, and the radius is twice the radius of the Earth. Okay, so we have to calculate the gravitational field. We need to know something about the force and something about its mass. It didn't give us force and it didn't give us mass. It just gave us density and radius. Okay, so we have to pull in other ideas here. Well, we can calculate the force with this equation, just substituting that into there. So this would be the mass of our planet, the mass of an object at its surface, and the mass of an object at its surface. That cancels out, and this is what we need to do to calculate the gravitational field. We do now have it in terms of its radius, which we have here, but we don't have it yet in terms of its density. We just have mass. So we have to bring in that density is mass divided by volume, or mass is density times volume, and then we can substitute that in here. One more thing first. It didn't give us anything about volume, but volume of a sphere is 4/3 pi r cubed. So we can substitute that into there and get this. So that was density times volume was mass. Now we're going to substitute all of that into right there. That the acceleration of gravity is all this fun stuff here. We can simplify it. The r squared is going to cancel out with the cube and leave just r. So this is how we're going to calculate the gravitational field at the surface of this planet, knowing the density and the radius. So that's just the same thing right here, but the density of Earth and the radius of Earth. Now I can go ahead and plug in that same thing, but now the density and radius of our new planet, that it was 3/2 the density of Earth and twice the radius of Earth. There's a 2 down here and a 2 there. It's going to cancel. Okay, there's a 3 here and a 3 there, but I'm not going to cancel that. I'll show you why here in a moment. I'm going to bring this 3 out in front here, and I still have the 4/3. The reason I didn't want to cancel those 3's is because the gravitational field of Earth had a 3 in it. So this is the gravitational field of Earth. This is the gravitational field of Earth. So we see that the gravitational field of our planet is going to be 3 times the gravitational field of Earth. Or just 3 times 9.8, 29.4 meters per second squared. That was a doozy, but maybe go through that again on your own. One last thing, maybe I should have brought this in on the previous video, but we have 2 different properties of mass. One is inertial mass. This person has resistance to acceleration. So if they're in an elevator and the elevator accelerates upward, they're going to weigh more because the elevator was pushing against their inertia. But we also have the other property of mass called gravitational mass. That if they're in an elevator and no windows, you can't see out, and all of a sudden we roll in a planet, well, that person's going to feel more weight due to the planet. And this is the equation that calculates with the force of gravity based on the gravitational mass. Okay, so this was the acceleration based on the inertial mass that we felt the additional force because this was accelerating, but the additional force was measured here because we rolled a planet under there. So just gravitational mass versus inertial mass, different properties of mass. And if that person's in the elevator and there's no windows, no doors, they could not tell if they weighed more against the floor because the elevator was accelerating up, or if we rolled a planet under there. No way that person would know the difference. And it's kind of an interesting conundrum. Anyway, that's a little bit about orbital mechanics.